So welcome to section 4.3, nearest points in convexity. After this, we'll move on into inner products and orthogonality in the Hilbert space setting. But in this section, as the title suggests, we'll find a closest point in a set to a given point with an eye towards the Hilbert space setting. Actually, we'll have some results that apply to Banach spaces as well. But Hilbert spaces are special cases of Banach spaces, so we're getting Hilbert space results ultimately. Now you'll recall the distance from a point X to a set capital Y in a normed linear space was defined as an infimum. The distance from X to Y is the infimum of the norm of X minus Y, where Y, lowercase y, ranges over all of set capital Y. Since it's defined as an infimum, you wouldn't expect there to necessarily be a point in the set Y that's nearest to point X. And in this section, we'll look at some conditions under which we do get such a single nearest point. Linear space is said to be convex if, for all X and Y, and any scalar alpha, such that, sorry, not a linear space, a set K in a linear space is said to be convex if for all vectors X and Y in that set and scalars alpha between 0 and 1, we have alpha X plus 1 minus alpha Y is an element of X. Now, your intuition in Rn is pretty useful here. Geometrically, what this means, a little bit more about geometrically in a second, is K is a convex set when we take any X and Y in K, all the points on a line connecting K are in X. When alpha equals 0, we're at point Y. When alpha equals 1, we're at point X. And we kind of move linearly between those 2 points, X and Y. About the geometrically thing, now, these are vectors, not points, although we'll continue to use the term points here. And we can make, in Rn at least, a natural relationship between points and vectors, but you have to put them in standard position for that geometric interpretation to hold. So just a little bit of warning about these geometric interpretations. It's good stuff if it accurately applies, but you got to be a little bit careful even in Rn with associating vectors and points together. That's fine as long as the vectors are in standard position. You're good to go. And the idea of lines connecting these points makes sense with that interpretation. By induction, if we had a bunch of points, x1 through x sub n in convex set K, and a bunch of scalars, alpha 1 through alpha sub n, which sum to 1, then if we took the linear combination of the alpha sub k's with the x sub k's, we'd also get this to be a point in K. So there's a more general implication about the convexity idea. Now, we're interested in conditions under which the nearest point to a given point from a set is unique. More specifically, consider this picture. So we got the point P, the point 0, 2, xy plane, and the set here. This would be the unit ball under the soup norm. We had this very similar picture a few sections back. And we want to find the distance from point P to this set, the unit ball. Of course, that distance is 1 with respect to the soup norm. So we're using the soup norm, and that's the reason the unit ball looks the way it does. But there's not a unique point in the unit ball that is distance 1 from this point P. In fact, if we'll take any point along this right-hand boundary, any point of the form 1 comma something, as long as the something is between -1 and 1, the y coordinate, then we'll get the distance between these points to be 1 under the soup norm. So there's not a unique point in set K that's closest to point P. Well, the problem is The boundary of this set is quote unquote flat. I'm taking my lead from Promeslow's terminology here. It's in some sense the idea that this is a flat a set with a flat edge. The flatness combined with a soup norm is what allows us to have multiple points that are the same distance from this point P. So what we're going to do is resolve that and introduce, as Promoslow says, introduce an idea of roundness in a formal way. First, a norm linear space X is strictly convex if, for any two distinct unit vectors, X and Y, we have the norm of X plus Y over 2 strictly less than 1. So we're taking unit vectors throughout, distinct unit vectors, adding them together, dividing by 2, and getting a vector of norm less than 1. I could probably put some pretty good RN geometric interpretations on this. How could you make the norm any bigger? Well, I actually need the vectors to be, I don't know, I'm thinking out loud here, kind of need those vectors to be parallel, have the same direction. If they had the same direction, then we could get a norm equal to 1 out of this particular sum. But we did say they were distinct vectors and also unit vectors. Vectors are not things with magnitude and direction. They are in Rn. Vectors are what the definition of vector space says they are, and oftentimes we've treated them as functions. But that idea is always looming in the background of magnitude and direction. Here you're saying they have the same magnitude because they're both unit vectors. So the only way they could be distinct, wink, very informally, is if they have different directions, I suppose. So they couldn't be scalar multiples of each other. We couldn't have them as parallel vectors, say. So there's an informal idea of how to interpret this strictly convex definition. It implies that if X and Y are boundary points on the unit ball, okay, so that'd be unit vectors, determine boundary points on the unit ball. Again, disclaimers and concerns about that geometric interpretation between points and vectors, but you know what I mean. So X and Y are boundary points on the unit ball. Then the midpoint of X and Y is not a boundary point because the midpoint of those two, technically the vector sum divided by 2, is in norm strictly less than 1. Well, that's not on the boundary of the unit ball. That's strictly inside the unit ball. So the boundary of the unit ball contains no line segments. Now, this is a discussion about the unit ball, not about arbitrary sets, but we could probably do some translations that are relevant based on vectors in the unit ball. And you'll see in the arguments we make, there's a lot of translations and some scaling that we'll do in the proofs of the 2 or 3 results we have. And this is the point at which Promoslow says the boundary of the unit ball is round. So it has this roundness to it in a strictly convex linear space. First result says, suppose X is strictly convex. So let's just keep that definition in front of us, meaning what's given up here. For any point X and convex set K, there is at most one point in K that is nearest X. So it doesn't guarantee the existence of such a point, but if there's a point, then there's at most one such point. Let's look at the proof. Okay, I think it's just one slide. We're going to translate some things. We translate point X and set K by an amount negative X. So we're going to subtract X from everything. So it's a nice rigid translation. It won't change distances in particular. So this nearest point idea won't be badly affected. I mean, it will involve some different vectors, but the idea of nearest point and showing a unique nearest point will not be affected. And we can always just translate back by adding X to the result. So we're going to translate by subtracting X from point X mapping it to 0, and subtract x from all the vectors in strictly convex set, or excuse me, convex set K. So we'll consider the set K minus x. It'll still be convex, but it'll be located at a different place. Then finding a point in K nearest to x is equivalent to finding a point in K minus x nearest to 0. X has been translated to the 0 vector. This is how set K has been translated. And finding a vector closest to the 0 vector is equivalent to finding a vector of minimal norm, a vector in set K minus x of minimal norm. So we've converted the question of nearest to minimal norm. Assume we get 2 points, y and z, in K minus x, both of minimal norm. Say the norm of y, and did I read that correctly? 2 points, y and z, in K minus x of minimal norm, such that the norm of y and the norm of z are both equal to a, and there are no vectors in K minus x of norm strictly less than a. But x is strictly convex by hypothesis, so that means if we take the unit vectors, y divided by a and z divided by a, so normalize these two vectors, take y over a plus z over a, add those unit vectors together, divide by 2, strictly convex space, you're going to get a resulting vector that has norm strictly less than 1. Then we can multiply through by scalar a, converting this into y plus z over 2 is less than a, y plus z over 2, that's an element of K minus x. I mean, K minus x was a convex set. We're taking, I don't know, the scalars alpha 1 and alpha 2 both equal to a half, so they sum to 1. We've used them as coefficients on the y and the z. So convex set, that will give you something else in that set. So y plus z over 2 is in K minus x, but y plus z over 2 has a norm less than a. And we assumed that y and z were of minimal norm, and that minimum was a. So there's a contradiction, and the contradiction comes in assuming there's 2 distinct points, y and z of minimal norm, 2 distinct vectors of minimal norm. So the contradiction of that minimality says the assumption that there were 2 distinct such points, such vectors must be false, and that's how we draw the conclusion of there's at most 1 point in K that is nearest to x. Okay, there's at most 1 point in K minus x of minimal norm, but then we can add x to everything and translate it back, and that gives us the at most 1 point in K nearest to x. And we'll do another proof where we do this translation stuff. By translating things to the origin, in a sense. We'll translate points to the origin, and sets will follow in a rigid way. Definition of uniformly convex. A norm linear space is uniformly convex if, for all epsilon greater than 0, there exists a delta greater than 0, such that for x and y in the closed unit ball centered at the origin, 2 different notations for that. The overline means closed. The radius is 1, the center is 0. So collection of vectors of norm less than or equal to 1. If x and y are in that closed unit ball, then we have 1/2 x plus y in norm is greater than 1 minus delta implies the norm of x minus y is less than epsilon. Definition, you can't argue with it, but I think we can extract a little bit of intuition out of it by thinking about these vectors as vectors in Rn. So the story here is we're taking 2 vectors, maybe they're unit vectors. If they were long under these constraints, they would be unit vectors, but their norm is less than or equal to 1, strictly speaking. And when we add those vectors together and divide by 2, we get a vector that I guess it's got a length close to 1. I want to think of it like that. So x plus y over 2 is a vector of length close to 1. But then that implies, the statement is, x minus y in the norm is less than epsilon. So the only way we can get, very informally here, 1/2 x plus y that vector to have a norm close to 1 is to have x and y close to each other. Well, that kind of makes sense with a magnitude and direction interpretation of vectors, one that's perfectly legitimate in Rn and maybe not in some other places, but it's good for motivation. So the only way we're going to get these vectors, x and y, both unit vectors, to have a norm when added together and halved close to 1 is by having those two vectors be close together. So they must be like almost parallel. I might want to think of something in terms of that, rather similar to what we discussed before. So here's our definition of uniform convex. Why even bring this up? This will be related to that nearest point stuff. And that's the big question in this section. A lemma, let's keep this definition running in the background, says if a norm linear space is uniformly convex, then it's strictly convex. Uniformly convex with the epsilons and deltas. Strictly convex was this property of adding two distinct unit vectors together and getting something divided by 2 that's of norm less than 1. All right, uniformly convex implies strictly convex. Let's look at a proof. Actually, let's look at a proof of the contrapositive. So instead of showing uniformly convex implies strictly convex, we're going to consider the contrapositive and show that not strictly convex implies not uniformly convex. So suppose a linear space is not strictly convex. So we need to negate the definition of strictly convex. That was the thing about having unit vectors where the sum divided by 2 was strictly less than 1. So we must have distinct unit vectors x and y such that the norm of the sum divided by 2 is greater than or equal to 1. The triangle inequality will cap it at 1. So we must have unit vectors x and y such that distinct unit vectors x and y such that x plus y over 2 in norm actually equals 1. Can't be greater than 1, triangle inequality. But, or excuse me, let epsilon be the norm of x minus y. So we're trying to find a bad epsilon. It's a bad epsilon if there doesn't exist a delta that satisfies the condition of uniformly convex. So we'll take epsilon to be the norm of x minus y. They're distinct vectors, so it's positive. No matter what we choose epsilon to be, for all epsilon, excuse me, no matter what we choose delta to be, that's the usual game. Epsilon is arbitrary, and then we pick a delta. We're showing no epsilon, or excuse me, this epsilon has no corresponding delta. So it is not true for all epsilon there exists a delta, is the logic behind it. So for this value of epsilon, no matter what we choose delta to be, so let delta be greater than 0, be arbitrary, then we have 1/2 x plus y, norm of. We got that equals 1. Well, 1 is greater than 1 minus delta. But we don't have the norm of x minus y less than epsilon. We have the norm of x minus y equals epsilon. So for this value of epsilon, there is no delta such that the condition we're looking for was 1/2 x plus y norm of greater than 1 minus delta implies norm of x minus y is strictly less than epsilon. So we violated that being the definition of uniformly convex. So we don't have uniform convexity. If we don't have strictly convex, then we do not have uniformly convex. Back to the notes, and maybe one final glance at what uniformly convex was. The norm of 1/2 x plus y greater than 1 minus delta implies the norm of x minus y is strictly less than epsilon. And we violated that for particular epsilon. It turns out every Hilbert space is uniformly convex. An easy little argument. Who's your favorite Hilbert spaces? Well, Rn, I like those. I'm comfortable with those. Really don't. I'm having a conversation about Hilbert space. I'm probably not too interested in finite dimensions, but when I say Hilbert space, that includes all the Rn and Cn spaces. Now, these are examples of Hilbert spaces as well. So the following result works in finite dimensions also. But this is pretty wild. Any Hilbert space, this says. Okay. We're trying to show uniform convexity. So we're trying to show this epsilon delta thing. Again, that's the definition of uniform convexity. So take x and y to be in the closed unit ball. So these are vectors of magnitude of norm less than or equal to 1. And let z be x plus y over 2. The parallelogram law, you'll recall parallelogram law holds in Hilbert spaces, came out of properties of the inner product. The parallelogram law states exactly this, well, rearranged. Take this last term, norm of x plus y squared, it's negative, move it to the left-hand side, and this reads exactly like the parallelogram law. We had the norm of x plus y squared plus the norm of x minus y squared equals this quantity here. Was the sum of the squares of the diagonals equals the sum of the squares of the sides of a parallelogram. This is where it got its name. But this is exactly a statement of the parallelogram law. Now here we know vectors x and y have norm at most 1. So this is at most 1 and this is at most 1. So in parentheses we have at most 2. 2 times at most 2 is at most 4. So this is less than or equal to 4. Z plus y, x plus y is 2 times z. Just we introduce the parameter z to represent this vector. So 2z equals x plus y. So we'll substitute that in as well. Here comes another 4. We can factor the 4 out and get 1 minus the norm of z squared. So we've got norm of x minus y squared less than or equal to, we picked up in the middle, 4, 1 minus norm squared of z. Now, if epsilon is between 0 and 2, then we're taking this particular delta value. First off, I'm worried about epsilon little, not epsilon big. I do have to cap the value of epsilon at 2, or else we end up getting square roots and negatives, and I can't use complex numbers for delta values. So sit tight. We'll take epsilon to be between 0 and 2 for now, and if you want to use a bigger epsilon later, well, you can do similar things. It'll follow similarly. We'll give a little explanation. But take epsilon to be between 0 and 2. That includes little epsilons for sure. And let delta be 1 minus the square root of 1 minus epsilon squared over 4. Well, if epsilon is between 0 and 2, then you're taking the square root of a non-negative number, and we're good. And choosing delta to equal that quantity. Why would you choose delta equal to this quantity? I must be trying to show uniform convexity. One more time, definition of uniform convexity was this. We want, in the notation we introduced, the norm of z to be greater than 1 minus delta to imply the norm of x minus y is less than epsilon. All right, well, there's our epsilons and our deltas. In the event that we've chosen delta to be this quantity, then we can rearrange this, maybe take the square root to one side, bring the delta to the other side. We'd have a 1 minus delta on one side and the square root on the other. 1 minus delta on one side, the square root on the other. Square both sides. It's an equality. So we get 1 minus delta squared equals 1 minus epsilon squared over 4. The square root's gone. We picked a square up on one side. And the norm of 1/2 x plus y, that was the norm of z, greater than 1 minus delta. Like we said, we want to take this as a hypothesis, and we want to show the norm of x minus y is less than epsilon. So we're at the stage of assuming 1/2 x plus y is greater than 1 minus delta. Next, we need to show this. Norm of x minus y is less than epsilon. Definition of uniform continuity, or uniform convexity. Okay, let's just keep this previous page somewhat in view. So 1/2 x plus y norm squared, that's a norm of z squared. Well, assuming norm of z is greater than 1 minus delta, norm of z squared is greater than 1 minus delta squared. And 1 minus delta squared we saw up here by our choice of delta. Here's why we chose delta to be what it is. That equals 1 minus epsilon squared over 4. So we'll insert that. Rearranging. Let's see, multiplying through by negative, I guess is what we've done. We'll put a negative in front of the norm of z squared. That'll reverse this inequality. We'll get a negative in front of this term. There it is. We'll multiply this by a negative, write it in the reverse order. So just multiply through by -1, and that produces this and reverses some inequalities. So it looks like we're getting closer. We got less than something involving epsilon, so we're on the right track. This can be rearranged to read 4 times 1 minus norm squared of z is less than epsilon squared. So what we've done here is take the 1 to the other side, group it together, and then multiply both sides by 4. So we've lost the -1 and the 4, leaving an epsilon squared on the right-hand side, and we've picked up a little extra stuff on the left-hand side. This implies norm of x minus y squared less than 4 times 1 minus norm of z squared. This we had from the parallelogram law right here. Norm of x minus y squared less than or equal to 4 times 1 minus norm of z squared. So we're using that parallelogram law part. We just saw this quantity is less than epsilon squared as we derive from that. So our choice of delta, it looks like it works. Take a square root of both sides, it preserves the inequality. And we get the norm of x minus y is less than epsilon. And that's what we were looking for. That's uniform convexity. Oh, and by the way, that was only good if epsilon was between 0 and 2. If epsilon's greater than 2, any delta works. Hey, you'd have the norm of x minus y is less than or equal to the norm of x plus the norm of y. That's triangle inequality. And x and y were chosen from the closed unit ball. So this is certainly bounded above by 2. And if epsilon is greater than or equal to 2, then, well, the result's trivial. So every Hilbert space is uniformly, has uniform convexity, is uniformly convex. How about some non-Hilbert spaces? Well, Promislow states that LP spaces, where P is between 1 and infinity, excluding 1 and infinity, the LP spaces are uniformly convex spaces. Doesn't get into a proof of it himself, but he mentions Carruthers' book, A Short Course on Banach Spaces, a book I'm not familiar with. A book I am familiar with, reading Simon's Functional Analysis from 1980, but a classic, has as an exercise proving that if P is greater than or equal to 2, then the LP spaces are uniformly convex. So there's some references on that, just a side note about some other spaces that are uniformly convex. Theorem 12, we return to the question about nearest points. So we're going to be given X a uniformly convex Banach space, by the way, that'll include Hilbert spaces, for any point X and a non-empty closed convex set K, there's a nearest point to X in K. So here's the conditions we need to get that nearest point. Uniformly convex, complete space, and we need to be dealing with a non-empty closed convex set. Then we'll get the nearest point behavior. Let's look at the proof. Similar to the first result we had, we're going to translate and more. We're going to scale some things too. As we did in the first proof in this section, let's translate by -x. So we'll take point X, move it to the origin, and we'll take set K and translate it to the set K minus X. Okay, so that puts the point at the origin. We're going to do one more thing. We're going to change the links of all the vectors. And again, all this stuff can be undone at the end to get back to the original setting. But we're going to scale all the vectors by the distance from x to k. So what this does then in particular is it makes the distance from the modified x, which has become the 0 vector, and the modified set k, which we're also denoting as k here, the distance from 0 to k equal to 1. We've done that, so we can look for a unit vector in set k. So translate everything by negative x first, and scale all the vectors by the distance between x and k, the original point x and the original set k. And we can, as they say, reduce the existence problem to showing that when the distance between 0 and k equals 1, and k preserves these other properties, it's closed and convex, for example, this implies there is a point y in k closest to 0. The closest 2 points will be a distance 1 from 0. Vectors that have distance 1 from the 0 vector are unit vectors. So it translates the question into find a unit vector in modified set k, translated and scaled. That is, well, it's a unit vector. Find a unit vector in set k, the translated and scaled set, and that unit vector will be the vector in k that's closest to 0. And we can translate that back to a point in the original set k by swelling things up by the appropriate factor and then translating, and take 0 and translate it to the point x. So this is just a modification of the problem to bring it into a cleaner setting. And we can simply now look for unit vector in set k. All right, the distance from 0 to k, by definition, is the infimum of the norm of y minus the point, 0 in this case, so just norm of y, where y ranges over k. We've said this distance, we've scaled things so that it becomes 1. We're taking the infimum of a set of real numbers. These real numbers are norms of vectors in set k, and the infimum of that set is 1. So by a property of infima, if we'll look at a quantity a little bit bigger than 1, so for any natural number n, consider 1 and 1 plus 1 over n. This is bigger than 1, but not much bigger than 1, not when n is large. We know by properties of the infima of a set, there's elements of the set between 1 and 1 plus 1 over n. If the infimum is 1, you go a little bit bigger, you'll find elements of the set. And formally is the way to think of it. Formally, it's the definition of infima in terms of a greatest lower bound. So we go a little bit greater and we run across elements of the set. The elements of the set will be vectors y sub n in set k. So for each n, choose a y sub n in set k, satisfying this norm condition by the very fact that distance 1 is defined in terms of an infimum. You can do this. Now, let epsilon be greater than 0 and choose a delta satisfying the uniform convexity condition for epsilon over 2. We're in a uniformly convex Banach space, so for epsilon greater than 0, there exists such a delta. That uniform convexity condition will give us, ultimately, we'll have something like y sub n minus y sub m in norm is less than epsilon over 2, with some lead-in role played by the delta. But the convexity condition will imply the norm of a difference is less than epsilon over 2 under certain circumstances. All right, we'll get there. Choose n, a natural number, where n is greater than 1 over delta. So in the beginning, epsilon's greater than 0. Based on the uniform convexity, there's a choice of the delta. Based on the choice of the delta, we're now choosing a capital N greater than 1 over delta. Suppose n and m are greater than or equal to capital N. Then let's consider the norm of y sub m plus y sub n over 2. First off, that's greater than or equal to 1 because y sub n plus y sub m, y sub m plus y sub n over 2. This is an element of set K. Set K was a convex set. So there's a convexity hypothesis used right there. And we've defined the distance using an infimum. So that infimum is 1. So we choose particular vectors in set K. Then we get some quantity and norm greater than or equal to 1. We're going to take 1 and write it as n plus 1 over n times 1 minus 1 over n plus 1. Get a common denominator here, simplify, and the arithmetic's correct. It cancels out and reduces to 1. And the capital N we're using is the one chosen up there. Hey, the one we chose up there, capital N, is greater than 1 over delta. Well, if I take reciprocals of both sides, that tells me 1 over n is less than delta itself. And of course, 1 over n is greater than 1 over capital N plus 1. Make the denominator bigger, make the fraction smaller. So this 1 over capital N plus 1, I know that is less than delta. We've got a negative sign in the way, so that'll reverse that less than inequality to give us a greater than, giving us capital N plus 1 over n times 1 minus delta is less than what we have above. All right, let's label that asterisk. We're going to need the fact that y sub m plus y sub n over 2 in norm is greater than n plus 1 over n, 1 minus delta. So around the end of the next slide, we'll use that. Define y sub n hat and y sub m hat by taking y sub n and y sub m and scaling them by capital N over capital N plus 1. Then we have the following. The norm of y sub n hat, and similarly for y sub m hat, is the scale factor n over n plus 1 times the norm of y sub n using the scalar property of norms. We had chosen y sub n, recall, to have norm between 1 and 1 plus 1 over n, the index there, different n's, no typos or anything, no, not I know of. Now, we can get a common denominator here. That gives us n plus 1 over n. We've chosen m and n to be greater than or equal to capital N. When lowercase n equals capital N, this reduces to 1. When lowercase n is bigger than that, this reduces to something less than 1. So that's how that inequality is established. It's based on the fact that f of x equals 1 plus 1 over x is decreasing. When the little n's get bigger than capital N, this gets smaller, which is kind of clear from the formula. But that gives us an upper bound of 1 on the norm of y sub n hat, and you can do the same thing for y sub m. It's defined in the same way. So we get y sub n hat and y sub m hat to be vectors of norm less than or equal to 1. They're vectors in the closed unit ball. Now, we take y sub n hat plus y sub m hat over 2 in norm, substitute in. Here's how we define y sub n hat and y sub m hat, as given above. Substitute in that common n over n plus 1 we can bring out front. We can bring the 2 out as well, but let's leave it where it is. Now we've got capital N over capital N plus 1, norm y sub n plus y sub m over 2. That's the thing we had a bound on in asterisk. Let's go back and look at it. Y sub n plus y sub m over 2 in norm. Y sub n plus y sub m over 2 in norm, greater than this quantity, n plus 1 over n, 1 minus delta. So let's make that greater than, substitution, greater than n plus 1 over n, 1 minus delta, substitute it in, still have this out front, cancellation here, we're left with 1 minus delta. All right, remember the convex assumption in terms of the epsilons and deltas. All right, so we've got two vectors, y sub n hat and y sub m hat, such that 1/2 the sum is greater than 1 minus delta. We had assumed, using the property of uniform convexity, that for that delta, this would imply that the difference of y sub n hat and y sub m hat in norm is less than epsilon over 2. We said choose delta such that the uniform convexity condition gives us this difference less than epsilon over 2. So that's where that comes from. And there we've used the uniform convexity hypothesis for the first time. So if we look at y sub n minus y sub m, no hats, norm of, those were defined in terms of the hatted y's as given here. We can bring the n plus 1 over n out. Y sub m minus y sub n in norm, we had that less than epsilon over 2. And this is less than or equal to epsilon. When n equals 1, this would be 2, and we get epsilon out. When n is greater than 1, this gives us a quantity less than epsilon over 2. And so strictly less than epsilon in those cases. But we've got y sub m minus y sub n less than epsilon for all m and n greater than or equal to capital N. That's a Cauchy sequence. So y sub n is a Cauchy sequence of elements of set K. X itself is a Banach space. Not sure we use that yet. Well, it's a Banach space, so this Cauchy sequence converges. Say it converges to y in the space, but set K is closed. I don't think we use that yet either. Hey, but a closed set contains its limit points. Theorem 2.2.a part 3, we've used so many times. So this limit point y must also be in K. We've chosen the y sub n's to satisfy this condition on their norms. So the vector y itself must have norm 1. N approaches infinity. This approaches 1. It's a continuity of the norm that we're using here. There's continuity of the norm. So y is a unit vector in set K, and it has norm 1. That means it's in modified and scaled set K. It's the closest vector to the 0 vector. That can be translated back and scaled back to give us a point in the original set K that's closest to the original vector lowercase x. So we scaled it back. We solved the scale problem by finding a vector of norm 1. The normalization let us look for that. And that's how we get the solution to the scaled problem, and then it can always be scaled back to give a solution to the original statement. All right, let's wrap up this section then. Subspace of a Banach space is also convex. I mean, spaces are convex or closed under linear combinations. So if we let M be a closed subspace of a Hilbert space and define projections of X onto M as the point in M nearest to X, we know such a point exists and we know it's unique with the results we have. That means we can use the projection idea to do the Gram-Schmidt process and talk about orthonormal bases in Hilbert spaces. So first off, we'll define this projection in terms of this nearest point stuff. So if M is a closed subspace of a Hilbert space, define the projection of X onto M as the point in M nearest to X. Such a thing exists by all this theory stuff we just went through. As a very geometric interpretation, and you know what? I'd like to deal with that in terms of inner products. So guess what's next? Orthogonality in dealing with inner products. So we'll see how to access these projections in a little bit more of a geometric way than all this stuff about nearest point things, though that too has a geometric interpretation. So I'll see you soon in the next section, and we'll look at orthogonality in the Hilbert space. Have a nice day.